you for joining us for this technical talk. We're here for a very interesting topic and excellent presentation, I'm sure, by two very good speakers. But first, allow me to give you a bit of introduction about IEEE and Power and Energy Society. IEEE is the largest engineering organization in the world. We have about 400,000 members. We are in 160 countries. And IPS, Power and Energy Society, is the largest society with IEEE. IEEE is source of most of the standards in industry and very well active society we have in Power and Energy Society. This event is organized by Power and Energy Society in WA. I can talk about Power and Energy Society for hours, but this is not the focus. I just want to say we have two major publications. One of them is Power and Energy Magazine. And Power and Energy Magazine, the latest issue is totally about Australia. So if you want to have a read, it talks about the different structures in the national electricity market and wholesale electricity market. So it talks about the two power systems, the regulatory framework, the challenges, and what's happening in the energy transition landscape. A really good article from Essential System Services in Western Australia, and also DER roadmap. So one of these articles is free to download if you want to know what sort of magazine it is, if you're not used to the magazine. But if you're a member, you can have the whole magazine, and I really recommend it. But let's go to our two speakers. Really interesting topic. The last one we did on inertia, Julius did, and it's got a lot of hits on YouTube. So I know it's really a good one to watch, and I'm sure this one will also be really a good one. With this short introduction, by the way, I want to also say that IEEE published today a paper on integrating renewable energy into the SWIS power system. That is online, and if you want to download it, it's free to read. It's really good read. This presentation is very aligned to that. So I'll briefly introduce the two speakers. Julius Susanto is a principal engineer with IEEE in Perth. He received his PhD degree from Murdoch University in electrical engineering and holds a graduate diploma in economics from University of Western Australia. Julius is an IEEE senior member and chartered member of Engineers Australia, and also received the 2020 Churchill Fellow Award. First speaker and the second speaker is Ali Reza Fereiduni, who's a senior engineer at the Australian Energy Market Operator and received his PhD from Curtin University in electrical engineering, and he's also an IEEE member. So Julius will talk for about 20 minutes, and then Ali Reza. Thank you so much, and please put your hands together for them.
All right, thank you everyone. So this talk is about the estimation and modelling techniques for real-time frequency stability assessment in a low inertia power system, and the SWIS, the Southwest Interconnected System, is really the case study for this. And it really just covers a lot of the work that we have been doing in IEEE over the last few years in terms of estimating inertia and then also doing frequency stability assessments. I'd first like to acknowledge that this meeting is being held on Aboriginal land and land of the Whadjuk people of the Noongar Nation. I pay respects to their elders past, present and future. So the outline of this talk, first of all, I'll talk briefly about the Southwest Interconnected System and changes to the generation mix in the last couple of years. Then we'll talk about system inertia estimation, how and why we need system inertia estimation, how we do it, the standard approaches, some of the problems with that standard approach, and some new ideas that are coming forth, including some of ours. And then next, Ali Reza will talk about the real-time frequency stability assessment. So we use these inertia estimates in a real-time control room tool to assess frequency stability on large contingencies. So first of all, the Southwest Interconnected System. So the SWIS is a medium-scale islanded power system, and it sort of serves 1.2 million customers in WA, Western Australia. And some of the big features of the SWIS is that, first of all, it's not connected to the national electricity market at all, so it's an islanded power system. We have to rely on ourselves. And I think most of the people in this crowd would know all about that. And it's a very big grid, so it's 261,000 square kilometres, bigger than the land area of the UK. But at the same time, it has a very small relative peak demand, so only 4.3 gigawatts, and compared to roughly 60 gigawatts in the national grid in the UK. And bearing in mind that 60 gigawatts has been going down recently, it's probably more like 50 gigawatts these days. So the gen mix from 2018 to 2020, so this is in terms of energy throughput, so rather than capacity. And what we see is that in 2018, a lot of coal, 44%, and mainly gas. So we're talking about 84% coal and gas. As we get towards 2019, you can see a reduction in both coal and gas. And last year, we're seeing a material increase in wind and reductions again in coal. And so gas has sort of stayed stable. And you can see in that yellow, the light yellow is rooftop PV. So that's all, it has been increasing quite a lot. This is what the picture looks like when we're talking about changes from Q4 2019 to Q4 2020. And you can see the black and the grey is reductions in coal and gas. So coal has been sort of reduced across the board uniformly, whereas gas, you can see, is reducing in the middle of the day following the solar profile. And you see the two yellow bits are grid scale solar and distributed PV or rooftop PV are increasing in the middle of the day, and we have a uniform increase in wind as a result of the two new wind farms, Yandon and Warradaji wind farms. I would be remiss if I didn't talk about rooftop PV, and rooftop PV has grown from practically nothing in 2009 to a huge number now. I learned today that this number is actually wrong, and it's more like 1.8 gigawatts, not 2.2. There's some inaccuracies in the DER registered data currently, but will be fixed. So let's just get on straight into system inertia estimation. Just wanted to set the scene with the SWIS. So what is system inertia to begin with? So inertia is traditionally defined as kinetic energy that's stored in all of the rotating masses of synchronous machines, both generators and motors in a power system. And it's basically energy that's exchanged with a power system. It's either released or absorbed whenever there's an instantaneous imbalance in generation and load. So when you have more generation than load, you'll see all the rotors speed up, and when you have more load than generation, you see all the rotors slow down, and then that energy is released into the system. And you call that the inertial response. So inertia is proportional to mass, size and rotational speed of the machine. So heavier, bigger, faster machine, a higher inertia. And so you can see some examples here. So big machine in a steam turbine, gas turbines, small machine like in a combustion engine, so they might have much lower inertia, and hydro turbines somewhere in the middle. And inertia is related to frequency, as we talked about. So ceteris paribus, so all things being equal, low inertia systems are more sensitive to frequency disturbances. So here, this graph just tells the picture. You know, high inertia, 20 gigawatts, let's say, not super high, but higher inertia, you have a better frequency response. As you get lower and lower, you get much lower frequency nadirs and a worse sort of frequency performance. So system inertia in the SWIS. So system inertia is actually very proportional to the size of the system itself in terms of generation capacity and demand. And so here are some estimates for system inertia all around the world. And I only stopped at ERCOT, so there are even bigger systems like PJM or the WEC in California, but you can see the system inertia in ERCOT ranges between 150 and around 400 gigawatt seconds. And then you go all the way back, National Grid, Nordic system. The NEM is somewhere in that range of 60 to 150 gigawatt seconds. Now, WA's grid, actually very small, so our range of is a lot smaller, sort of between 10 and sort of 28-ish gigawatt seconds. And we would probably be smaller than New Zealand were it not for the fact that they're interconnected. So, you know, individually they're smaller, but they're interconnected by a HVDC interconnector. So you could say that the SWIS is a low inertia power system in the scheme of things. Here we are. And not only is it low, but it's been going lower over the years. So here's a plot from 2017 to basically now, or August 2021, and you can see it's really slowly declining. And I will say this is generator inertia, so it's not even looking at load inertia or anything, we're just talking about generator inertia, and I'll talk about that a bit more. And it's been declining because of increased penetration of inverter-based resources, solar and wind, that is coming into the system, and a lot of rooftop PV. And here's sort of the histograms. As I said before, it sort of ranges between the 10 and the 25, 28 mark, but most of the time it's sitting around that 15 to 20, you know, or 12 to 20 sort of range. The maximum inertia we've ever had, as far as the records I've seen go, it's about 27.2 gigawatt seconds, and the minimum is 7.8 gigawatt seconds earlier this year. And so this is minimum without a contingency as well. So we had a contingency, it'd be even lower. So why do we even need to estimate inertia? So could we even just measure it? You could potentially measure inertia if we had a real-time measurement, every single generator, every single synchronous machine connected to the system. If we knew what the inertia constants for those machines were, we could actually measure it in real time. So you have all these generators all connected in the power system. If you had a measurement whether or not they're connected to the system or not, you could say, yep, you could add them up, all the inertia constants and come up with a inertial value for the system. However, that's obviously pretty onerous in terms of every single small embedded generator. So if you have a diesel genset connected to the system, that provides inertia. If you have every synchronous motor, like mills and so forth in mines and that provides inertia. So industry, mining, commercial facilities, they all have sort of inertia in the system. And that would be pretty hard to actually achieve in practice. So we'd say it's pretty cumbersome, and usually what we do is we estimate what inertia is out there. And here are the sort of standard approaches. What I talked about before was that real-time generator inertia monitoring. So what we actually have is the breaker status of all the large synchronous machines in the system. We know when they're on and when they're off, and we also know what their inertia constants are. So, for example, we know if a Muja unit is on, or a Nugent Quinara or a Blue Waters unit, and we can add them all up and we track it. So it becomes basically a SCADA point that we track over time. And then what we also do is we make a correction for load inertia that we've basically based on a linear regression from estimates we made in the past, given load and what we found load inertia to be. So what we found when we've done this in the past is there've been really two blocks, two clusters, and we use the bottom, the blue cluster, because it's just a bit more conservative. So real-time generator inertia monitoring is fairly standard amongst all the TSOs and ISOs around the world that do this. So, you know, ERCOT do it, AirGrid do it, National Grid, the Nordic TSOs, and here's some examples of some screenshots of their system. So, you know, we're not alone in doing this kind of thing, and it's fairly standard. However, the load inertia estimates are probably less standards, and the total system inertia estimates are not as standard. I know the NEM don't really do it. So the other way that you can measure inertia, the most common other way, is after a disturbance. So once a generator trips, for example, you can get all the traces, the high-speed traces, and you can try to estimate what the inertia would have been given this frequency trajectory after that trip. So you use what's the linearized swing equation and some high-speed fault data. So here's what the linearized swing equation looks like. Not very good on this screen, but here's the inertia estimate. You have to calculate what the rate of change of frequency is, and you have to know what the generation loss is. So usually you know what the generation loss is. You know, you trip a 200 megawatt blue wattage unit, you know it's 200 megawatts, so you can just plug that in. And then you calculate the rate of change of frequency based on the frequency trace itself. There are some caveats here, and this is only valid under certain conditions using a linearized swing equation. So first of all, the disturbance has to be instantaneous. If you start trying to feed in a ramp, then this no longer applies, because what you'll end up having is you'll have primary frequency response starting to act and so forth, and these sort of simplified formulations no longer are valid. The system frequency and its first derivative, the rate of change of frequency, have to be able to be measured accurately and high temporal resolution. So when I say high temporal resolution, really talking about high-speed fault recorded data. You can't use, for example, SCADA, 4-second SCADA to do this, because it's just too blocky. It's too, it's not, the resolution is not high enough. And the onset of the disturbance has to be accurately determined. You have to know when t equals 0 is when the actual trip happened. And so that's why high-speed recorders are useful, because you can actually know exactly when the trip occurred. And the effects of load relief and primary frequency response are neglected. So in the timescales that you're looking at, in that first half a second or so after a trip, you're assuming that there's no load relief and there's no primary frequency response. So no one's sort of started going acting yet. Which, you know, when you think about this, when you start having fast frequency response come through, this becomes a little bit more challenging. So we use the post-disturbance estimates to tune that linear regression, so we can create a real-time estimate of system inertia. And that estimate is will get used in the real-time frequency stability tool that Ali will talk about. And that's sort of how it all fits together. So one of the first things I really want to sort of point out is that the rate of change of frequency needs to be estimated. And it's a very key component. And you can't actually measure it, the rate of change of frequency, because it's the first derivative of frequency, and all you're measuring is frequency itself. And ideally what we would do is we take the high-speed frequency measurement and we take sample by sample rate of change of frequency, which would be like taking one sample, subtracting it from the previous sample and dividing it by the sample resolution. That would be the most ideal way of doing the rock-off measurement or estimation. But unfortunately, quite a few problems with that sample estimate, and not least which is the noise that you get from the transducer. You'll just end up with getting a lot of spurious numbers that come out of that estimate. And secondly, you might even have transients in the frequency trace, maybe because of a network fault. And thirdly, you might have oscillations from generators oscillating against each other. So your frequency trace is not clean, and in fact, often you have all these different features in the frequency trace. And if you started trying to use that, all of a sudden you'll think that you've had a rock-off of like 4 hertz per second. And incidentally, this is actually why a lot of protection relays trip, is because they trip on rock-off because they think that the frequency, the rate of change of frequency is a lot higher than it actually is, because they're trying to do these estimates in real time. And so the basic thing is that you need to do some kind of smoothing on the frequency signal before you can work out a rock-off. And there's two really standard practices that are done. First of all is to use a sliding window. And so our standard current practice is to use a 500 millisecond sliding window to smooth out the frequency trace. So you can see in the picture on the right here, you have some oscillations in the frequency trace. If you were to choose a very small window, you'd actually get a higher rock-off than was actually there due to the oscillations. And then you choose a 500 millisecond, you smooth that a little bit. So 500 milliseconds was actually a recommendation from the European grid. We'll probably talk about this a bit later, is about why that may or may not be good for the SWIS. And the second method that was introduced by IEEE was the polynomial fit. So you basically, instead of trying to just use the raw frequency trace, you actually fit the frequency trace to a n-order polynomial. So in Inui's problem in Japan was that there was just quite a lot of oscillations in the frequency trace. You can see all these oscillations there. And so he found that using a fifth order polynomial would fit quite well. This is back in the 90s. So that's the second sort of standard approach, if you will, for doing this. However, there's some sort of issues with the standard approach, and I'm just going to go through how do you even... Oh, so first of all, let's talk through some of the issues. What if the contingency is not instantaneous? You have to just discard that event. So if you had a boiler trip, for example, that just sort of ramped down and it failed, then you basically can't use that event in an inertia estimation, because what you'll end up seeing is a rock-off that's very slow. And then when you start plugging that rock-off back in, you'll see inertia that's very, very high. And so that's clearly wrong. And then, yeah, what if there was a fast frequency response? Then we're assuming that there's no primary response, and we're assuming it's negligible in the first sort of half second to a second after the event. So if you started having a battery response come through, then this would be difficult again to use these kinds of techniques, because they would be confounded by these effects of PFR. I guess this is a real issue here is what sliding window length or polynomial order is actually appropriate. Like, one of the main problems here is that the estimate is actually very sensitive to the choice of window length and polynomial order. We're using 500 milliseconds, but how do we know that's actually correct? We've just taken a recommendation from the European grid. And how do we know that fifth order polynomial would work? So we've done a few sort of studies here, and one of the studies we did was, first of all, we just did it on some simulations like in a computer simulation, and we're using like just very standard IEEE, like a 9-bus network. And the reason we want to do this is because we know everything about this network. So we know its system inertia, we know the load relief, we know the contingency size, we can characterize this thing completely. And when we do a contingency, so this is the simulated response, a beautiful, it's like a classic case of a contingency. And we started, suppose we're using the sliding window technique, and we just changed the window length on the x-axis. And we know what the inertia is. In this case, it's about 1,500 megawatt seconds. Then you can see that as you increase your window length, your inertia estimate gets worse and worse. In fact, you overestimate it. You could overestimate it by almost a half or more. So if we use 500 milliseconds, you can see here that it's about 2,000 megawatt seconds, so we're more than 400, 500 megawatt seconds higher than our actual inertia.
Excuse me, Joe, this is to measure the total system inertia?
It is, yeah.
Yeah. Not just generator inertia?
No, well, we know what that is, yeah. So
yeah.
We're always looking at load inertia as well, yeah. And so with the Inouye method, then the polynomial order starts flip-flopping around after you get to around the 20 order polynomial. And one of the reasons for this to happen is because you start overfitting the data when you get to high polynomial orders. And so this one's pretty good around 20-ish, let's say. However, suppose we used another network. So this is in this case the New England 39-bus network. Same sort of thing, exactly the same algorithms. And here is the frequency trace after a contingency. And you can see, in this case, there are some oscillations. So this is one of the interesting things about this that we wanted to highlight was all of a sudden 500 milliseconds doesn't look so bad anymore with the sliding window technique. And in fact, if you go too low, it doesn't work because now you're picking up these oscillations. And on the other hand, using the polynomial fit, it gets very bad because now you're overfitting for all these oscillations in the polynomial fit. So there are some material problems with trying to use these methods when you have different sort of configurations in your network and different contingency types. So this is an approach that we've been trialing in AEMO, where we basically, rather than just using the frequency trace, we're trying to fit it to an actual model. So we have a system frequency response model, and we are trying to fit system inertia and load relief at the same time. So we get 2 for 1 here, and to the high-speed frequency recorder data. And so this is what we're trying to fit. This is the differential equation for the system frequency response model. I'll just talk through it so it's not so daunting. But the first point to note is that we know what the load is there. So what we're trying to actually, that's the pre-disturbance load, so we know that, and we're trying to estimate D, which is the load damping or the load relief factor. So we actually have the contingency as a trace. So even if it were a ramp down, we can see it as a ramp down, and we can plug it in because we're using now more of the data rather than just a simplified swing equation. We also know what the aggregate PFR is, so we're just basically adding up all of the primary frequency response traces from all the generators that we know that provide PFR. And what we're trying to estimate is the system inertia and the load relief factor, and we're fitting all that to a known frequency trace. So that's basically the idea is we're trying to use more of the swing equation, because the linearized swing equation only uses this bit and then this bit at t equals 0. So we're trying to just use more information that we've got from the high speed data. And we just did the proof of concepts with the IEEE 9 bus and the 39 bus, and you can see it's pretty close. Like, so where it was 1522, we're getting 1589, and the load relief factors were also pretty close. And also on the 39 bus, we're not too far out, probably slight overestimate, but it's better than the other ones where you don't know where you are at. How do you choose the polynomial order or the sliding window? In this case, you're not choosing anything. You're just running it through the algorithm, and then off you go. So it probably gives you a better order of magnitude estimate. So some of the shortcomings, I guess, is that you actually require a complete data set. So if you've got some high-speed data that's missing, it's just sort of more difficult to use unless you try and put dummy data from past events to sort of simulate that. So you need to have the contingency trace and all of the traces from the PFR providers. If you don't have a PFR provider, then basically if it's not measured, then it's considered as load relief. That's basically the upshot of it. So the other approaches, they only need the contingency size and the frequency trace, but they're potentially less accurate.
Can you explain the load relief? Is that load trips or is that controlled load shedding?
Yeah, good point. So load relief is a sort of property of induction motors primarily, where the power output is actually proportional to frequency. So as frequency drops, their torque drops, and then the load just goes down. So it sort of relieves the load, if you will. You know what I mean? So you get a reduction in load because induction machines are reducing. So I mean, this is mainly more material to industrial plants and mining and like houses with air cons. They tend to use inverted air cons, so that doesn't really have that much load relief. But so you don't get a lot of load relief in the residential loads, but mainly from mining loads. And if you were to look at, for example, bidding up desalination plant, they have a perfect load relief curve because it's all just induction motors, and they're about 4 or 5% relief here. So some other approaches is this is a really interesting and innovative approach to measure inertia online, and what it does is actually tries to perturb the power system. So you're actually injecting active power injections into the power system, and then trying to measure what you get on the other end. And so what you're perturbing it with is actually an oscillating frequency. So this is what it looks like. So you've got a modulator, so it could be a big battery, and it's injecting a sinusoidal frequency into the power system at some megawatt value. And then what you can do then is you can get very sensitive sort of PMUs, measurements of the frequency in the power system, and then you can isolate out that frequency that you're actually oscillating at. And with that, you can then use your simplified swing equation, because you actually have every point, which is, you know what injection you're using and you know your rock off, because you're actually measuring it from the frequency trace. And so it's a controlled way of measuring or estimating inertia rather than using disturbances. So you're actually causing a disturbance, but just a small one.
How big should the injection be?
Well, they think it's up to 0.1% of the system size is what reactive technologies have sort of can go down to. I don't know the answer to this, actually. It's something I'd like to explore a bit more, is what kind of perturbation would give you a real accurate result, and what is just noise. So it has to be above the noise floor, and I think it depends on your system or how much it's moving anyway. So this is, again, it's patented and commercialised by a UK firm called Reactive Technologies, and it's been sort of trialled in the UK. I'm pretty sure Japan tried it on a small grid, and I think the NEM are now trying it to a certain extent. All right, so that's all I had, and I'll pass you over to Ali Reza. Thank you.
Thank you, Judith. Thanks, everyone. So in section 2, so I'll present about the tool we've got in AMO. So all the outcomes from our research. So the outcome is our tool, which we use to predict the frequency. So how to assess frequency stability in real time? So what we've done, so we've developed a tool. So the name of the tool is real-time frequency stability. So it is actually in the control room, and we've been using it for a year. So when we say frequency stability, what do we mean? So by frequency stability, the requirements we consider is, this is a trace of a frequency, a typical one after a large contingency generation loss. So the aim we're trying to achieve is, we're not supposed to hit stage 1 offals. The threshold we've got in the technical rules, the number is 48.75. So the idea, or the minimum point of the frequency trace after generation loss shouldn't touch the offals threshold. So that's one requirement. Another one, so that's the frequency nadir, and that's the offals threshold. And another requirement we've got is rock off. So rock off shouldn't or must not be above 0.5 hertz per second. So that's another requirement which we need to achieve. And also frequency should recover to a quasi steady state value. So as you can see, a very nice recovery. And then after that, so AGC will bring back the frequency to nominal value. So that's the rock off. So we measure and we consider to control. So the tool outcome. So the tool outcome is exactly like this. So, but this is a hypothetical trip. So the tool, what it considers is, it recognizes what is the largest unit of the system, and if we were to lose that unit, what would happen to the frequency? So if we see any response that not within the requirements, we try to, for example, one of the remedial actions is to provide or provision more spinning reserve. So we've got other remedial actions as well, but I don't want to delve into it. This is just a quick background, so for the tool. So the inputs of the tool is SCADA data, or real-time data we've got and available through SCADA. So a bit of background stating the obvious, what is frequency? Frequency is the heartbeat of the power system. So to me, frequency is like an indicator. So it's like a balance between generation and load. So when we've got generation more than load, so frequency will be higher than the standard. So what is the standard in SWIS? 50 Hertz. So if generation is less than load, so frequency will be lower than 50 Hertz. That is a simple fact about frequency. And it is very important to control frequency because equipment and devices connected to electricity might get damaged if frequency goes outside the technical band. So we've got normal operating bands and other technical envelope. So we have to control the frequency, and we've got measures for it. So one of the reserves we've got to control the frequency is definitely droop or spinning reserve. In this slide, I want to talk about what we need to consider to predict frequency trace in real time. So this is actually a real event, so we've had in the past. So normal operating band, so based on technical rules, the normal operating band, if frequency goes below 49.8, so that frequency will be outside of normal operating band. So what is the aim? We're not supposed to hit stage 1 offals. So we had a contingency size of 217, inertia size around 16 gigawatt, and system load at the time was 2.4 gigawatt. So this is the, so at that time we had a contingency, and this is the measurement, so frequency measurement. Now, if we want to predict that, so what we should consider, so I'll go stage by stage. First thing we need to consider, Julius mentioned, is inertia. So we need to estimate the inertia correctly. So first, assume that we've got only inertia. What happens to frequency? This is the frequency trace. So the second, so on top of that, we should know about load relief. So if we consider system inertia and load relief, this would be the frequency trace. So that's not enough. So there are other components into it as well. So just 1 point, system inertia here includes load inertia and generation inertia. Another component is AGC. Will AGC help? Not so much, because the time constant is high. It's around 8 to 20 seconds maybe. So next one is droop or spinning reserve. So if we add that to the trace, the pink one, so we're getting very close. So for our purpose, this is enough. So if we add all together, AGC, droop, load relief, system inertia, we get exactly like the measurement. That said, we need to have all the components estimated accurately. So, but for our purpose, for the tool, we need system inertia, load relief, and droop. Why do we need a tool to monitor frequency stability? So let's talk about regulation a bit. So spinning reserve provision rule. So AMO operates power system as per WEM rules. So the rule we've got, it says 70% of the largest generator contingency should be available at all times. As this is about spinning reserve rule. So this simple provisioning rule has been serving AMO for ages, and it was enough. But nowadays, we've got challenges. Why? We've got renewables being connected, are also DPV. So we've got huge amount of DPV connected to the distribution system. So we've got less synchronous generators connected to the power system, so less inertia, and all the reserves we were receiving from those generators, and now we've got less. Why? Because they are less online. So some of the challenges, as you can see listed here, low system inertia. So if system inertia declines, we will have higher rock-off and leading to lower frequency nadir, harder to control the frequency. And we will have high contingency size. For example, we've got huge amount of DPV. If we lose a portion of that DPV on top of a utility size generator, so that contingency size will be very high as well. So that leads to higher rock-off, leading to lower frequency nadir, meaning that it is harder to control the frequency or to arrest frequency fall after disturbance. Slow droop response, as I said, again, when less synchronous generators are online, so they provide, so the droop, because previously they provide droop or primary frequency, so at the same time, so the ramp rate where the ramp rate was higher, but now because we've got less units online, so the ramp rate is slower. That again leads to lower frequency nadir. So our solution, so based on the research and all the works we've done, so the tool we've developed, in real time we consider all the real data like system load, system inertia, and we consider largest contingency size. That contingency size could be a generator with largest megawatt or a generator with largest inertia. So what we do is we predict the frequency. If we identify that for any largest generation contingency, so we will have a non-secure state, or we will breach the requirements, we try to fix it in real time. So the structure of the tool, this is an overall structure of the tool. So I'll start from part one. From all the SCADA points, we recognize what is the largest unit, and we feed that into the tool. And then we've got inertial response. So we use single frequency model or single mass machine. So we consider SWIS as a single machine. So all the generators connected to a single bus. Part four, so we've got droop model. So all the generators providing spinning reserve. So we did model every single of them. So we receive the droop response from each unit separately. And we've got system demand response or system interruptible load. We've got some loads that they trip if frequency goes below a certain thresholds. So system demand response is part of spinning reserve. It's not part of offloads or under frequency load shedding. And load relief calculation, I guess Julius covered that, and load inertia as well. So system inertia includes load inertia and generator inertia. Okay, let's talk about inertia model. So as I said, we use single mass machine model. So we consider SWIS as a single machine. So this is the structure, detailed structure of, it's a very simple low order differential equation. So the SWIS is treated as a single machine with the combined kinetic energy of all the online generators under the assumption of a uniform frequency. So this is the equation for the single frequency model or swing equation. So we've got delta P. Delta P is the imbalance in power and system inertia. So we've got generation inertia, or the sum of all the inertia of the generators all together from SCADA system, and we know the system load, and based on the equation we've got for load inertia calculation, we estimate that, and we know which unit is the largest, and we know the contingency size of that unit. So all together we feed it into swing equation, and then we can calculate frequency nadir or minimum point of the frequency trace tool predicts. So why we use single mass machine? Because this is an actual event. So we've got high speed data. So different substations in SWIS. So this is frequencies measured at for this event 20 substations. As you can see, not much difference. It means frequency is almost the same all over SWIS. So it means frequency is uniform across SWIS. And that's another event. Frequency is measured at 18 substations. Again, same concept. So that proves that using single mass machine model is valid. Now, the next important part of the model is the troop model. So as I said, we consider the turbine governor model of each machine separately, and we did calibrate each separately based on actual measurements from past events. So how to model turbine governor model of the spinning reservoir providers? So we had to decide whether we want to use a detailed model or simplified model. This is just an example of a detailed model, a custom model for one of the generators. You can see it's very complicated if we wanted to use it in real time in terms of, so it's very complex, and in terms of a computational burden that would be very hard. This is just for only one generator. So if we consider like 20 generators solving all the differential equations at the same time, that would be a lot. That's another example. So that's a typical gas T2A model again. So just wanted to point out, considering detailed model is it's not recommended. So and another thing is that when we compare the response of the detailed model and simplified model, given what we want and what we aim for, so there is not much difference because we're not doing offset studies to consider the limiters, for example, temperature limiters or acceleration limiters. So this is the simplified troop model we considered. So as you can see, we measure, so this is the delta F, or frequency deviation, coming from swing equation. So delta F is calculated by swing equation, and we've got droop deadband, which is 25 millihertz in SWIS, and droop gain, so based on technical loss, 4% is the droop gain, and we've got maximum minimum based on whatever a unit can provide, like how much spinning reserve they can provide up and down, and the lag block. The lag block is the heart of the turbine governor, or simplified turbine governor. So because we had to calibrate the parameters to get sort of similar responses, considering detailed model and also measurements. And this is the overall model considering all the turbine governor models. So as you can see, we've got individual models, like separate models for each unit, and then we add all together, and that we call that a troop response, or overall troop response. And the parameters we've got, time constant and proportional gain. So we had to like tune these parameters to get similar response. Model calibration. So what you can see here, we've got 6 different units. So from left top, so open cycle turbine. Black trace is the measurement, actual measurement for a trip we've had in the past, and the blue one is the trace we had after the calibration for that particular unit. So you can see some oscillations here or some spike. These are inertial responses because we're using swing equation. It's already considered because we consider all the inertia all together. So what we needed to do is to match it with PFR, or spinning reserve, not inertial response. So on the top we've got responses from gas turbines, and on the bottom we've got from steam turbines. And after building everything, so we had to test it. So against real measurements. And the outcome of the tool is the frequency trace. So the tool predicts the frequency. So for different events, so black one is the measurement frequency trace, and blue one is the final product of the tool. So as you can see, it's pretty aligned, and the nadir is a bit lower, which we wanted because we wanted to be a bit conservative. And tool in operation in the AMOS control room. So this is our tool sitting there. So that's the main page of the tool. On the top, you can see a green color means secure. Why? Because so that's the trace for that time. So we had blue waters as the largest contingency at the time, and the megawatt was around 200 megawatt. So that's the frequency trace. Frequency nadir predicted was around 49.05. So indicating the system hypothetically is secure, and everything is fine in terms of rock-off and frequency nadir.
How often do you run it? How is it? What's the
2 minutes.
every 2 minutes?
Every 2 minutes. Yep. So some components into it. So the green dashed line is load relief, demand response or system interruptible load. We've got primary frequency response. All together, that would be total frequency response. So the contingency size, we have 280 here. So we have to provide exactly 280 to arrest the frequency or to reach a quasi-steady state condition. So in here, we had a contingency. So generation power was less than load. So frequency was dropping, and we had frequency responses ramping up. But by the time it reaches to the amount we've lost, so you see frequency nadir. That point means generation is equal to load. So you see rock-off is 0 rate of change of frequency, because frequency is an indicator between which shows that if there is a balance or not between what? Generation and load. So at that point, generation is equal to load, so you get an idea. And then the response is, in terms of quantity, is higher than megawatt you've lost. So frequency starts to recover because generation now is higher than load. And then at the end, you provide what you've lost, and then you reach a quasi-steady state point. Thank you so much.
So maybe, Julius, you can join Ali Reza and we ask questions, right? I have a question. So we lose inertia because renewables are displacing synchronous generation. If we leave a headroom with renewables, let's say 5% of their output, for fast frequency response, how much would that response be valuable in terms of inertia from synchronous generation?
There is a trade-off
Okay.
between fast frequency response and inertia, and it gets you some way. So definitely, the lower your inertia is, the more valuable fast frequency response is. And you're well aware that the new reformed market has speed factors in place where it will actually incentivize faster responses at low inertia times and high contingency times. So yeah, if you kept the headroom, and I think this is now in the new market that should be possible for a renewable energy plant to actually provide spinning reserve if they were able to prove that their headroom was able to provide it, and they would be given a fairly high speed factor if they can do it very quickly. So if we're talking about solar farm, right? If you can just ramp up within a second, then surely you get a high speed factor. Ian.
Julius, thank you, gents, for your presentations. I must say I was a little surprised there was no mention of duck curve, because that's where a lot of the inertia problems are, and the idea of that. But anyway, that's another thing. On the first question is on the demand charts that you put at the very beginning of your presentation, Julius. Was that operational demand, or did that include behind the meter satisfied load?
It was all operational demand. Yeah.
So does it include the behind the meter?
No, it's all net off.
It's all only generation
Yeah.
that's seen. So how much would that change if you had those charts? Because, obviously there's an awful lot of satisfied demand, particularly in the middle of the day. On an energy basis for the whole year, it's probably quite a lot, huh?
It is huge, yeah. You wouldn't see it duck, actually. You just see it, like on a cloudy day, what you normally see is actually pretty flat in the middle of the day. And the cloudy day is indicative of what you're getting through solar. So you actually sometimes even see hump at lunchtime. So yeah, you do get a lot out of the solar behind the meter.
Then you mentioned about fast frequency response in validating equations. We don't really have much fast frequency response in terms
Not
of
yet.
the SWIS.
Yeah.
It's a real deficit. We've been screaming for it for the last 5 years and nobody's listening. But anyway, finally it's coming through. But why does it matter if the fast frequency response eliminates the impact of the contingency? Why do you have to worry about inertia if you've got fast frequency response?
Yeah, inertia is still necessary unless it could be so fast that it responds instantaneously, because at some point the frequency is going down. Your fast frequency response is actually responding to the frequency signal. So it still needs to measure the frequency, then needs to do something.
So it's
Your
the latency
inertia-
of the signal getting to the
Exactly.
battery terminals.
The inertia is going so fast, so low, you're already in uffles before your fast frequency response can even
So
do
then,
anything.
does that revalidate the argument of maintaining synchronous condensers to improve the system inertia?
Could be
regardless if we're
condensers,
gonna
it could
have
be
batteries?
virtual inertia, it could be any other,
Right.
whatever it is, there needs to be something there. Until, of course, you get to completely IBR. If you're completely 100% inverter, then frequency doesn't mean anything, because the inverter can create whatever frequency it wants.
Right.
So is inertia, synchronous inertia, naturally instantaneous, right?
It is. Yeah.
Inherent to the
Yeah,
power
'cause
system.
it's just, it's there, it's inertia.
It's energy is released or absorbed, yeah,
Through energy,
through the
yeah.
motion of rotational energy, yeah.
Now, another thing, you didn't mention over-frequency response, load projections that could occur. Does your tools take that into consideration? Are you using that as a...
It can, but it's not a real material problem for us, because through the generator performance standards, all wind farms, all things have to droop down on an over frequency. So there's actually quite a lot of, if you've got a generator running above minimum generation, you've actually got headroom down. It's the other way around that's more of an issue, where you on the under frequency side, because you actually might have all the generators running at maximum, and so you don't have any headroom up. Right, so that's what you need a provision for. But generally speaking, we don't have a problem with over frequency response. We've actually never had a frequency deviation above 50.5 hertz. So it's never been an
The
issue.
final question is, the event that happened about 9 months ago, or maybe a little longer, time flies these days, where half the SWIS inverters dropped out due to an earth fault up in the North Country somewhere. And they all dropped out because they sensed it and it was unprepared for. Would you consider that to be a bigger issue? Because not only do you not get the exported supply from those inverters, you also get an increased load because the inverters drop out and the household load is automatically a big problem. Would you say that was a bigger problem than inertia, natural inertia in the system?
No, they're all the same problem. But I mean, and in fact, we actually consider that because Blue Waters here was only running at 197 megawatts, but you could see the continuous size was around 280. That includes the about almost 80 megawatts or over 80 megawatts of tripped solar PV that we're allowing for. So we have a real-time measurement of how much DER is in the system, and we take a percentage of that as how much we think it could trip off. And that was actually calibrated on that event that you're talking about was it the 1st of January or the 2nd of January? I can't remember. Yeah.
Yeah, first, I think. Yeah, I don't recall the date, but yeah, we did change the tool after that. So, it's incorporated in there, yeah.
Some of the battery manufacturers talk about being able to offer virtual inertia, which is, Fred, you mentioned. Is that instantaneous?
It is.
As well?
Yeah, so
How is
what
that?
they're offering is
Yeah.
basically a grid forming technology,
Yeah.
where a lot of these inverters now, they're grid tight, so basically they need to sense the grid frequency to stay synchronized, and they need to follow the grid frequency as such. So they get a voltage waveform and they have what's called a phase lock loop to stay in synchronism with the grid frequency. What these grid forming inverters do is they have their own frequency reference. So they can actually act a lot like a synchronous generator. And in fact, a lot of these grid forming inverters have what's called virtual synchronous machine mode. So they have controls that look a lot like a synchronous generator, provide inertia in a very similar way. It's almost like a swing equation inside their controller. And yes, so they can provide. Now, the limitation is actually on power electronics, because whereas a real synchronous machine is just a heavy piece of metal, right, spinning around, this thing now you're actually limited by your converter IGBT, you know, your transistors, because you can only give out so much current. So you're probably limited on how much inertia you could get from one of these virtual inertia machines.
Is that likely to change? Like, as people talk about grid forming, like being more common in the future, maybe? Is that because the power electronics are getting better, or?
No, you just have to or you can probably turn any of these into grid forming. So it's mainly a software change. But if you have lots of them, then that's just everyone now providing inertia, which is nice. All these little inverters providing inertia, so you just get more of it. I think that's where the future's probably headed.
So would they ramp back the inverters for normal functioning operation, and then when they need the power, they've got some up their sleeve for additional...
Yeah, it's a good question, because if they're running at full, they can't do it, right? Like they basically max out. So yeah, but it is for the first, only for like, inertia only happens in the first sort of like 1 or 2 seconds. So they don't need a lot of megawatt hours to provide that. But they do need the headroom in terms of their power capacity to actually provide that in that inertia. Yeah, you're correct. I think some of these ones can overload a little bit, so that they can provide 20% overload. Yeah, most inverters. So yes, but in principle, if you want everything to have virtual inertia, then you probably need to back off a little bit or oversize your inverter.
It also depends how much energy you can get from the solar panels out there.
Yeah, so you're right. This is mainly for battery-backed systems. Yeah. Yeah. So
the energy should be there, whereas in like synchronous generators, so we get it from rotating mass.
Exactly.
That's
That
correct.
is all, about all your actually frequency sampling, did you use any specific sampling range for sampling the frequency, or any?
You mean the high speed data?
Yes,
Or?
the highest speed.
Yeah.
The highest speed.
Yeah, it's 10 milliseconds.
So 100 hertz sampling rate.
Yep, thereabouts. Yeah.
So is it enough for 50? Because your frequency changes around half.
Yeah, the dynamic is time constant is.
It's quite large for
Yeah.
frequency. Yeah, we're not talking about transients here. Yeah.
And just in practice, if you've got, I don't know, 140 megawatts of spinning reserve, and it suddenly jumps for a reason to, it's saying, well, really you want 260 now. What's actually happening in real time at the moment? Like if it sits there saying, well, your spinning reserve requirements, 260, and all we've got scheduled at the moment is 120. What are you actually doing about it in real time?
It really depends, like which units are providing and how much inertia we've got. So you might have, for example, two small, like not small, but 2 units in min-gen, so they can provide full headroom. So they're sitting at 25, they can provide each 100, right? So 2 gas units, that would be 200 of spinning reserve. So that shouldn't be enough, maybe from tools perspective.
So in reality, the units are there, and you kind of think, well, there's plenty of headroom in these. We know we've got it covered.
Yeah, but in terms of
So
speed
the
of
market's not
response,
necessarily paying for it because the market's just paying for its contracts. But you're actually looking, going, we've got plenty of, like if you've got 9 units providing, 500 megawatts of synchronous generation, but actually their max capacity is more like 1200 megawatts, you'll sit there going, well, they're going to respond. Is that what's happening in real time? I'm just wondering what system management are doing about, in response to changes in that calculated number every 2 minutes.
It doesn't change that often, to be fair. Like,
Right.
you're talking about generators that are sitting there, usually the largest contingency of base load, so they just sit there for a long time.
Yeah, so there's plenty, so in reality there's plenty of headroom, as you say, there's plenty of reserve. It's
But
not
when
really a
something
problem.
changes, so then it goes red, then you've got to do something about it. That is
When
true.
would it go red?
So usually what happens is, a lot of the time when there are changes in solar and wind, the machines that provide spinning reserve are also providing load following. So they're moving up, and we actually just get reducing the amount of reserves in the system. And then maybe what will happen is, at the same time, you've got a generator ramping up, so their contingency size is becoming very large.
Yeah.
And all of a sudden, this might flag up and say, you better do something about it. And in which case, you can do one of a few things. So what Ali said was redispatch, change your generators around, or if you can do it, you can also reduce the contingency size, or even turn on a new GT.
So is the emerging problem now less about spinning reserve and more about actually droop response itself? You know, like you've got to have that fast response in reaction to an event. You know that if you survive the first 5 seconds, probably the spinning reserve's kicking in and saving you anyway. It's all about that first few seconds that you're trying to now go, all right, we need to have that first 5 seconds covered.
Pretty much just five. So droop response and spinning reserve are the same thing.
Yeah,
in this sense,
but,
yeah.
I mean, the AGCs, the units are setting their deadband and they're setting their min-max droop responses in those parameters. You know, I can recall that Blue Water had a problem that if it provided the technical rules exactly frequency droop response, the problem is it would swing. It would actually get larger swings under and over power because fuel's being fed in, it responds, it withdraws, and actually the modelling showed it could actually swing out of control, you know, trip off ultimately. So of course they just had to deaden their droop response to not let that happen. So, you know, that's probably still it doesn't matter what the rules say, the physical unit will ultimately say, hey, you shove too much fuel in, then back it off, then shove too much in. And so they can't let that happen. And that's the same with the collar units now as well.
But that only happens in the absence of momentum, of inertia in the system. Because if you've got inertia in your system, you're not going to have these oscillations.
Yeah, I mean, before PV was on the grid, it was still a problem for droop response, was still a problem for blue waters and collar units. That it could swing, and we could see it happening. So we'd say, well, we can't. The units providing the initial response, then backing off, and then providing another response, and the swings got bigger and bigger. So we actually had to say, well, no, we can't actually meet the pure requirement of technical rules without risking that the unit will trip itself off. Anyway, I just think it's interesting that the droop, and also, you know, coal units with a small deadband, they just can't sit there responding to those small deadbands. So there was all these kind of practical problems, but I wonder if some of them are being solved in one way by having more inverter-based technology, especially if we get some batteries, of course, and you know, we might actually have less of a problem with thermal units. I just noted, I'm just looking at that thing, spinning reserve, you know, you've got 9 units on with 600 megawatts of headroom in their generation capacity. Do you need to do much if there's that much sitting there?
No.
Yeah.
No. Often you don't need to do that much.
Yeah.
If you've got like enough spinning reserve available. But for some circumstances, because we consider DPV tripping on top of largest contingency for some like transmission line faults, sometimes could be an issue when it is volatile, and we've got, as Julius mentioned, sometimes we've got several units on LFAS, so they provide LFAS and eating spinning reserve megawatt because they are almost the same thing. So could be some issues sometimes, not all the time. Yeah, you are right. If you've got 9 units providing spinning reserve, yeah, definitely there is no issue.
Yeah.
So looking forward, if we would see then that as in the case of generation, the generators are going to be more prolific and smaller. So these problems will be less, because you lose a generator and it's
Yeah.
biggest generator in the future might be.
That's the ideal
12
case.
15 megawatts.
There are two things
Then
into
you want
it.
to go
One,
transmission issue.
yeah, we've got less, the generation contingency is less, and if they all provide spinning reserve, they provide at the same time, so the ramp rate would be higher, so that definitely helps us.
That's good, yeah. Peter?
Look, this is really interesting. It really explains a lot about what's being done at the moment to manage that volatile frequency equation at the moment with renewables. I'm thinking a year ahead, and I'm thinking what I read today in the AEMO report and reliance on things like potentially big battery coming out, which provides some form of fast frequency response. But also notice that your application here in estimated frequency can't quite manage fast frequency response yet, or just the equations get distorted. If that's so. What? Two things. Have you set any performance requirements for fast frequency response that this big battery would need to provide? And have you got in train, the capability to actually estimate what it would be in real time to see whether it's adequate or not to manage your frequency?
Good question. So when I said that it wrecks the equations, it's more around the inertia estimation side. This can incorporate the fast frequency response part of it, so that shouldn't be a problem. It's more around our inertia estimates using our standard methods become a bit, they get distorted, so we would have to use some alternative, like some new approaches. But to answer your question, not at the moment. I think it's being discussed currently around what performance standards the battery will have in terms of how fast they should go, what the droop setting should be, etc., etc. So I think that's a three-way conversation between Synergy, Western Power, and AEMO.
When do you hope to gather all that information?
You better ask Matthew next to you.
Yeah, it's in progress.
I'm just
Training.
curious because it was mentioned, highlighted today in that report. So.
Yeah, it's a good question though.
You kind of touched on it there, talking about big battery, but there's been a huge amount of DER and 90% of it's PV rooftop. What would the effect on frequency stability be if some of that DER became behind the meter storage? If there was, an economic shift and suddenly batteries are worth money and then everyone's putting them in, would that have a positive or
Huge
negative
effect, yeah, huge positive effect. I think in Germany or in one of the European states they're using behind the meter battery now for frequency response, and there was a big event earlier this year, and basically
Electric vehicles responded.
things were responding, and it was very good.
Yeah.
And was that a centrally controlled BPP or essentially not?
I don't believe so. No, I think it was like just homes.
Plus
and-
inverse settings.
Yeah.
Connected, yeah. Was, I guess, coincident, all the electric vehicles were connected and supported the grid after the separation.
That looks like another topic for the next presentation.
Yeah.
Because we are reaching 6:30, so thanks you again,
Thanks
Alireza and
everyone.
Julius, for your presentation. It was very informative. Cheers.
Thank you.